Welcome to Study Loop.
So in this problem, we have a square. So that's this red shape right here, and it's lying in the XY plane. It has length L, and there's a magnetic field right there that is coming out at us. In other words, along the Z axis. And over here, I've drawn the same picture, but from the side. So the X axis now is coming out at us, and the Z axis, because it's going up, so we see the magnetic field going up, and the square has rotated by some angle phi. And the question asks us a number of things, the first of which is, what is the torque when the loop has rotated an angle phi and is traveling at an angular velocity omega? So first of all, we should remind ourselves that omega is d phi dt, right? The angular velocity is the rate of change of the angle. So let's start by determining the torque. So there's two sources of torque. There's the gravitational torque and there's the magnetic torque. So let's start with the gravitational torque. So we're going to start with the torque due to gravity. So if we think about the side picture, the gravitational force is down, but as far as torques are concerned, the component of gravity that provides the torque is the perpendicular component, right? So the component of gravity that we care about is actually this one, because the other component doesn't provide a torque. So if this angle is phi, you can see that that angle is going to be phi. So if that angle's phi, what that means is the gravitational force we're interested in is going to be the cosine. So we get the cosine of phi. Now, we have to be a bit careful because the different branches of the square are going to experience different torques because they're different distances away from the axis. But if you remember, so here's the square, here's the head-on diagram. Gravity acts as if it were at the center of mass of an extended object. So the centers of masses of the three sides of the square that are rotating are here, and each one has mass m over 4 because it's a square, so they each get m over 4. And then this distance is L over 2, and this distance is, of course, that's still L. So now we can calculate the torque. So remember, torque is basically distance times force. So for the two sides, so this one and this one, we have that the distance away is L over 2, and then the gravitational force is mg cos phi, where m is m over 4. So m over 4g cos phi. And then we also have the top part, that's that one. It's a distance L away, with a mass m over 4, and then we have g cos phi. So the total gravitational torque is going to be 1/2 L mg cos phi. So that's the gravitational torque, and clearly that torque is going to be like this. So it's pulling the square down like that. So that's the gravitational torque. Now, what about the magnetic torque? Magnetic. So first of all, why is there a magnetic torque? Well, the flux through the loop is changing, right? So as it rotates, the amount of magnetic field that's going through it is decreasing. So if there's a change in flux and it contains a current from from Faraday's law, then there's going to be a torque. So from the side, it looks like this. So again, there's the loop after it's rotated a bit. The magnetic field is up, and the magnetic moment is in that direction. This angle is going to be phi. So you can check again that this angle is going to be phi by the same kind of geometric arguments, and therefore the torque is I A B sine phi. And for our particular case, A is L squared, so this is I L squared B sine phi. So now we just have to figure out what the current is. So the current is going to be given by the voltage divided by the resistance, right? That's Ohm's law. And then the voltage is going to come from Faraday's law. So we've got 1 over R times the rate of change of magnetic flux. So what's the flux? Well, the flux is the area times the magnetic field times the component of the magnetic field that's actually going through the loop. And you can see from the diagram that that is going to be the cosine. So that's again L squared B cos phi. So therefore the current is 1 over R times L squared B times the derivative of cos phi. So the only thing that isn't a constant is this phi, right? But remember that the derivative of phi is omega. So by the chain rule, the derivative of cos phi is going to be omega sine phi. So this is L squared B omega divided by R times sine phi. And that's just, again, that's just the chain rule with that derivative. So substituting this into here, we have that the magnetic torque, I'll call this the magnetic torque, is L to the 4th B squared omega over R sine squared phi. And the way that magnetic torque works is that a loop will always rotate in such a way that it wants to align its magnetic field with the external magnetic field. So its magnetic moment is pointing out like this. And since the external field is pointing up, it's going to try and rotate like this to align those. Therefore, the direction of this magnetic torque is actually counterclockwise. It's the opposite as the gravitational torque. So the net torque is actually going to be the difference. So we conclude that it's 1/2 L mg cos phi minus L to the 4th B squared omega over R sine squared phi, and that's the torque. Part B asks us for the angular acceleration. So Newton's second law in rotational form tells you that the torque is equal to the moment of inertia times the angular acceleration. So to find the angular acceleration, we just need to divide the torque that we found by the moment of inertia of the square. So to calculate the moment of inertia of something, we have to perform an integral, and it's the integral of r squared dm. So we're adding up chunks of mass all over the length of the object. Now, m, well, probably the easiest way to think about this is that we have a density, right? So a density is equal to the mass divided by the total length of your square. So the total length of the square is 4L and the total mass is M. So the density is M divided by 4L. And therefore dm is just going to be essentially this M divided by 4L times dx. So actually, this is M over 4L times the integral of r squared dx, where this integral is taken over the length of the entire square. So for the sides, there's two sides. And there we're just integrating y, actually. Y squared from 0 to L. And then for the top part, we have M over 4L integrated from 0 to L. But now because the top part is entirely a distance L away from the axis of rotation, we just have an L squared there. So there's actually no variables. So computing this integral, you should find that the moment of inertia is 5 over 12 ml squared. And that's also something you can look up in a table of moments of inertia, but that's sort of the quick way of showing how you would calculate that. And then we can just apply our formula. So the angular acceleration is, again, the torque we found from part A divided by that moment of inertia. So it's 6g over 5L times cos phi minus 12 b squared L squared omega divided by 5m r sine squared phi. And C asks us whether the additional torque slows it down, and yes, it does. So the magnetic torque slows down the loop, right? Because it's being applied in the opposite direction as the gravitational torque, so it's going to rotate slower than it would if there were no magnetic forces involved. And D just asks, is energy conserved? Well, energy is always conserved. So energy is always conserved. But we should note that if you have a resistor, actually resistors heat up, right? So they dissipate power. So therefore, some energy is going to be lost to the power dissipated by the loop itself, because it is providing resistance. And that's the full solution to the problem.